Okay, welcome back everyone to the second part of today's lecture, where we quickly discuss a bit further the Local Density Approximation, or LDA in short, and the Generalized Gradient Approximation, or GGA in short, which are basically rank 1 and rank 2 of the Jacob's ladder, which we discussed in the previous part of today's lecture. Okay, let's start with the Local Density Approximation. So the Local Density Approximation builds basically the foundation for virtually all exchange correlation functionals for the higher ranks. So it's quite a fundamental concept. And the idea of the LDA is we start from a unified electron gas or homogeneous electron gas where all the electrons are distributed across the system. And if we do that, then we split again our exchange correlation contribution to a exchange part and the correlation part, whereas the exchange part, sometimes also called Slater exchange. And because we are in a because we start from or we are within the homogeneous electron gas framework, our Slater exchange basically looks like that and depends on that third order square root. And the density here, if you basically multiply that out by integrating over it, you get for the density the density depends in that case then from the fourth divided by 3 order. So basically sometimes you see that it depends on n r to the power of 3 divided by 4 divided by 3. You know what happened to the correlation part, and that's quite interesting because the correlation part is still unknown. So the best we have here are quantum Monte Carlo simulations by Ciperli and Aalto, done I think in the 1980s, and various LDA functionals are basically parameterized to those data. So LDA in short, it depends on the electronic density at point R, and LDA is only defined for spin unpolarized systems. But now you may ask, okay, what happened if we have a spin polarized system? So what happened with the spin? So in that case, addition is made. It's called Local Spin Density Approximation, or LSDA, in short, to LDA. And LSDA actually now takes the different spin configurations into account. So now LSDA depends on the density of the spin up and the density of spin down, and the same as here. So, and we have a parameter basically which describes the degree of spin polarization. It's sometimes called setter, whereas basically setter equals 0 is a completely spin unpolarized system, and it's setter equals 1 basically means a fully spin polarized system. If we now go one step further and go to the Generalized Gradient Approximation, right? The idea here is that the exchange correlation functional depends not only on the point R but also on the point R prime. So therefore, the exchange correlation functional within the GGA approximation depends on the density, here, as well as on the gradient or derivative of the density. And again, we do a split again for the exchange and the correlation contribution, and the exchange contribution again depends on one part on the Slater contribution from LDA. So that's why I pointed out that LDA builds the foundation for quite a lot for nearly all exchange correlation functionals, even at higher ranks. And then the second part here is basically where we take the gradient of the electronic density into account. So in that functional here we have this reduced density gradient parameter for given spin sigma, and here we have the spin the gradient of the electronic density. And in the case of a homogeneous electron gas, the reduced density gradient parameter, it goes or basically is 0. So the whole term here becomes 0, and then GGA equals the LDA exchange contribution. So that's basically it with how to formulate LDA and GGA based exchange correlation functionals, and in the next part we will then discuss the need for dispersion interaction corrections in DFT.